Welcome to Chapter 2. Here are the topics we will be discussing. So the first part is sort of historical. And then we'll move on to the periodic table and end up with naming. So the Greeks invented science, came up with science. Democritus, where our word democracy comes from, coined the term atmos, meaning indivisible. So at some point, all matter is indivisible. That's where the word atom comes from. Aristotle later on said that if you break down matter, you'll always come up with fire, earth, air, and water. And that's it for atomic theory for the next 2,000 years. When a school teacher by the name of John Dalton proposed the atomic theory. He resuscitated an ancient idea. Dalton's theory has 5 postulates. The first one is that elements are the smallest unit of mass. They are the indivisible, undergo a chemical change. Matter is made up of elements and atoms. An element is something that it's the same for all of that element, and it has the same properties. And so it is only one type of atom that makes up an element. Atoms of one element differ in properties from atoms of other ones. A compound is 2 or more elements combined in a small whole number ratio. So Dalton said that when elements combine, it has to be a whole number. It can't be H2, H1.50. It has to be H2O. Johnny Dalton's 4th postulate. The 5th one is the conservation of mass during a chemical reaction. Johnny Dalton said that all that happens in a chemical reaction is the atoms rearrange themselves, but they don't go anywhere. The 5th postulate of Dalton's atomic theory. So we see evidence that his theory is correct when we look at a penny or a bunch of pennies. We see that on the microscopic level, it's only copper. And all the atoms of copper behave exactly the same way. Here's a copper oxide, which looks completely different. It looks black. And now you're seeing copper 2 oxide. So this is a 1-to-1 ratio of copper to oxygen, but always a whole number ratio. His theory provides a lot of macroscopic evidence that we see on a microscopic explanation. The microscopic explains the macroscopic. Here's some evidence for Dalton's theory collected by Joseph Proust at around that time. He took 3 separate samples of isooctane. Isooctane is the gasoline that you put in your car. And he measured the carbon to hydrogen ratio in 3 separate samples and found that the mass ratio was always the same. Isooctane behaves exactly the same way and is exactly the same thing in every different compound named isooctane. We take it for granted now, but back then, this was a big deal. The law of multiple proportion states that when 2 elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. Again, this is a lot of verbiage, but basically it's explaining that when elements combine to make compounds, they do so in whole number ratios. In other words, atoms exist. It can't be a fraction here because there's atoms that are doing this. Here is copper with a greenish color to it. The copper is brown here, and so its properties change depending upon the ratio that it combines in. In one case, it's 2-to-1 copper. In the other case, it's 1-to-1 copper, and they can have very, very different properties. But again, always whole number ratios, usually small. So this brings us to the miracle of chemistry. If you take some sodium metal, here it is, you can cut it with a butter knife. It's very soft. And you put a tiny piece in water, it will explode. It will explode. Here's chlorine gas, toxic. The first chemical weapons were made of chlorine gas, and they combine in a whole number ratio, 1-to-1, to make salt, without which we cannot live. So the properties of the compound are very, very different from those of the element. So in the 2 centuries subsequent to Johnny Dalton, we've made a lot of progress, and we now know that atoms can be broken down into smaller things. It's not totally indivisible. And here is Johnny Dalton, excuse me, J.J. Thomson. And he experimented with cathode ray tubes. Now, there's a link here. I wonder if I can right-click on it and it will come up. I know the links work and they're very good. Sometimes you have to copy and paste them, which is annoying, but you can do it. If I didn't have to record this presentation, I would. Something wrong with PowerPoint. I can't get the links to work. But here it is.
What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube.
Empty.
The only thing we have are 2 electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background.
So that fluorescent screen, it's like that glow-in-the-dark, glow sticks. It's the same stuff. It just glows when it's lit up, and when it's lit up. So it's like a battery. This is a circuit, and there's nothing in there. It's an evacuated tube. So they're essentially zapping empty space. There's the power pack. So when you connect the circuit, look at what happened.
Coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes.
Look at that. A beam. What is that? J.J. Thomson did not know. No one knew what that, there's nothing in the tube. You sucked out all the air. What could possibly be happening? Very, very mysterious. We have an observation. We need a hypothesis.
That fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field
Now this is interesting.
to this cathode ray.
Look at this. What do you think? He's got holding a magnet there. A magnet is a dipole. It has a positive end and a negative end. All magnets are dipoles. Look at what happens when he holds it up to the cathode ray. Just like playing around with it, right?
And he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and see what the other pole does.
What?
This is my
It's repulsing the ray. It's repelling it. Huh.
You see what's happening to that beam. What does it appear as though it's happening to it?
Remarkable, isn't
Moving,
it?
it's being repelled, isn't it, by the magnet?
Now, what do you think is going to happen when he flips it around?
Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there?
So attracted on one side, repelled on the other side. Remarkable, right? And he discovered the electron. That's what the ray is. It's a stream of electrons. The electrons were negatively charged. And they were much, much, much smaller than atoms and elements. So he had discovered something smaller than an atom, the first subatomic particle to be discovered. So if these were negative, he proposed that there must be another particle which is positively charged to counteract the negative charge. So he predicted the existence of protons, another subatomic particle. So we have a new view of the atom. And this is a wonderful connection into how science works, because we have an experiment, observations, measurements. The observations show the existence of electrons, the predicted existence of positive things. How does that all work itself out inside an element? What exactly is the internal structure of an atom? And you're seeing two competing conceptualizations, two competing hypotheses. The first is called the plum pudding model, in which the element is a giant piece, not a giant, a piece of plum pudding, with you're seeing the electrons and the protons scattered around like being baked into some plum pudding that you're seeing on the left. And then a competing model, kind of a solar system model, has it that the positive charges are toward the center of the atom and that the electrons form a ring, like a ring of Saturn, around the centralized protons. So which is it? Which is it? And this is how science works. Two hypotheses, two explanations for the same thing, and now you need to do the test. You have to test the hypothesis. And so both of these were tested out, and this leads to, as we'll see, the next famous experiment. But before that, before the testing of these models, here's another view of the plum pudding model. We have a great American scientist, Robert Millikan, who has a high school named after him in Long Beach, California, where he was from. And he did a very, very interesting and famous experiment, which is very, very elegant. And I just want to point that out to you. Here it is, the figure from your text. But I want to go to this animation here. I have previewed these, so I know they're good. Nice and short, too.
Millikan's oil drop experiment. British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method.
So Millikan is trying to figure out how much charge is on the charge of the electron. Because once he could figure that out, then you could determine the mass of the electron. They knew it was much, much smaller than an element, but they had no idea what the value was. So here is the Millikan oil drop experiment.
Method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment.
Look at this thing. He's got his hand on an atomizer, like what you spray your plants with, but he's spraying oil droplets, very misty oil droplets. These two gold things are two electrical plates that are connected to the power supply. So he's got an electric field here. And he has finally some X-rays. Here are the X-rays. He's blasting the oil droplets with X-rays. And what that did, he was trying to ionize, vaporize the oil droplets. And he also had an eyepiece here that he could look through, and by changing the voltage, he could determine how fast the electrons, the oil droplets, which were basically electrons because the X-rays stripped off the electrons, he could look in there and see when the oil droplets remain suspended. He exactly tuned the voltage up, voltage off, going very fast, turning up the voltage, slowing the oil droplet down until it wasn't moving, it was suspended. At that point, he had measured the charge on the electron. Absolutely stunning, stunning experiment. Hope you guys appreciate it.
Method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E. That is, Q is equal to NE, where N is equal to 1, 2, 3, and so on. Using the value of charge of the electron, the mass of the electron, ME, was then determined by combining Thomson's value of E by ME ratio. The value shown is the value of the mass of an electron.
Tired of your food going to waste? Freeze drying could be your answer. There are a few different ways of preserving food.
Quite a remarkable experiment. Sure you will agree. So what we're seeing here is different oil drops, and you see 4.8, it's all 10 to the minus 19, 4.8, 3.2. It's always a multiple of 1.6. That's the unit, that's the charge on the electron. When we say -1, it really means it has that much charge. When we say -2 or -3 or whatever it is, we mean it has that much charge. It's the fundamental charge on the electron. Extraordinary. And using what J.J. Thomson had did, he was able to figure out the mass of the electron at 9.1 times 10 to the minus 31 kilograms. Now we'll see the significance of that in a minute. So that's Millikan. Then comes Ernie Rutherford, and he is really testing the plum pudding model and the planetary model. And so here we have another video. Well, these are really good. I'm going to let you guys, hopefully you will, click on that. It's very short, but it's a wonderful animation. I'm just going to explain it to you. This is a lead casing. Inside the lead casing is a source of radioactivity, and the radioactivity produces an alpha particle. And he shot, it's like think of it as a machine gun. And he shot this ring here is plated with film that glows, just like we saw in J.J. Thomson, that it glows when something hits it. In the middle is a sheet of thin gold foil. Thin, like aluminum foil thin, very thin. The luminescent screen that catches all the particles. So he took a machine gun and he fired it at the thin gold foil. Now, if the plum pudding model is correct, if you take a machine gun and you shoot it through this thing, they should basically, and these things are very tiny, it should go right through it. That was the expectation, that all of the alpha particles would go right through. If the plum pudding model is correct, it predicts that the alpha particles would go right through the gold atom. But look at what they found. A lot of them did. Most of them did. A very small number were deflected. What? That means the only way they could get deflected, if you take a machine gun and you blast it with aluminum foil, is if there is something very, very dense in there. And he had discovered the nucleus. The nucleus. Both of these models are disproved. Both of them through this experiment, which shows a different internal structure of the atom that is the one we have today. A small, very dense nucleus that contains most of the atom's mass. The protons are also located in the nucleus. So this result, the implications, the fact is that that small, very dense nucleus means that atoms are empty space. Mass is empty space. In fact, 99.9, and it's even 99% of the atom's mass is contained in the nucleus. Where the neutrons, those were discovered later, 1930 or something, where inside the nucleus is where the protons and the neutrons are. But it's 99.99%, and the atoms, the space between the nucleus and the electron is 99.99% of the volume of the atom. This nuclear model of the atom, again, has the stunning conclusion that matter is basically empty space. So an analogy, which I think brings this point home, is that the relationship between the size of the nucleus and the volume of the atom is like a blueberry at the 50-yard line on a football field. The blueberry is the nucleus. And again, that is about the same relationship to the size of the atom, the size of the nucleus inside an atom. Pretty extraordinary, really. So here you are seeing the difference in the masses in kilograms. We saw 10 to the minus 31 before. It's the same unit. They've just shifted the decimal place to put everything to minus 27. And when you look at the masses of the three particles, the proton, the neutron, and the electron is, what is that? How many decimal places? 1, 2, 3, 4 is 10,000 times smaller than a neutron or a proton. 10,000 times smaller. And that the neutron and the proton are about the same size. So that is nice. That is what's convenient about atomic mass units, is you can easily see the relationship between the masses of the three objects. And on the final column, you see the charges on the three objects: -1, +1, and 0. So the relationship to a proton and electron is like a baseball to a grain of sand. That's how much bigger the proton is than the electron. So next we come to isotopes. Isotopes. An isotope is atoms of the same element that have a different mass. How can that be? Is that a violation of Johnny Dalton's rules? Some ways, yes. What it is an isotope, it's the same element, but a different number of neutrons. So a different number of the neutron inside the nucleus. So our modern periodic table that you see behind me, that you will have handy when doing the homework problems, arranges elements on the periodic table according to their atomic number, which is given the symbol Z. The atomic number is Z. The atomic number is the number of protons in the element. It is the defining trait of an element and determines the identity of the atom. For example, any atom that has 6 protons is carbon. Can't be anything else. Doesn't matter how many neutrons and electrons it has. If it has 6 protons, it's carbon. So here you're seeing a nice, convenient periodic table. Look at the atomic number. Z is above the element symbol. 1, helium, 2, lithium, 3, 4, 5, and so it goes in order. Helium has 2 protons. Lithium has 3 protons. Beryllium has 4 protons. Boron has 5 protons, and so on and so forth. The number of protons, the atomic number Z, defines the element. An isotope, again, it's the same element with a different number of neutrons. Here is helium, always with 2 protons. Here is aluminum, always with 13 protons. All elements are found in the neutral state. So that means if all elements are neutral, that means that the number of electrons has to be equal to the number of protons. That must be true. If you had more protons than electrons, you'd have a net positive charge. And if you had more electrons than protons, you would have a net negative charge. So if all the elements are neutral, once you know the atomic number Z, you also know the number of electrons. So now you can go back to this periodic table. How many electrons are in lithium? Well, it has 3 protons, so therefore it has 3 electrons. You feel me? So if you know the number of protons in the element, you also know the number of electrons. The total number of protons plus neutrons is called the mass number A. So we have 2 things, the atomic number Z and the mass number A. The mass number is P plus N. Therefore, P plus N minus P, or the mass number minus the atomic number, is the number of protons. Excuse me, the number of neutrons. Protons plus neutrons minus protons is the number of neutrons. So there you see, A minus Z is the number of neutrons. Now, on this periodic table, the mass number is not given. The mass number is not given. Only these numbers here below the symbol, 58.69, 63.1, and so forth. That's the atomic mass, which is related to what we're talking about, but not equal to what we're talking about. So there's another notation, that's used to give the mass number A. So here's an example. How many protons and neutrons in an atom of sodium? The mass number is 23. So therefore, 23 minus 11 is the number of neutrons. And so it has 11 protons because its atomic number is Z. If it has 11 protons, it has 11 electrons. So between the mass number and the atomic number Z, you can figure out how many electrons, protons, and neutrons are in the elements. And there are some problems like that, of course, on the homework. So now let's talk about an ion. An ion. We know what an element is. What is an ion? An ion is an element that has removed an electron, 1 electron or 2 electrons or 3 electrons. So if you strip off an electron from a neutral atom, what's the charge? You remove an electron. It's a +1 charge, because now you have 1 more proton than electron. Each electron has a -1 charge. So if there's 1 less electron, there's 1 more proton. So if you have 11 protons and 10 electrons, what's the charge? +1. If you have 10 protons and 9 electrons, what's the charge? +1, same answer. What if you have 9 protons and 10 electrons? What's the charge? -1. What if you had 9 protons and 11 electrons? What's the charge? -2. You guys see the pattern? The charge on an atom is the number of protons minus the number of electrons. Atoms acquire charge by losing or gaining electrons. They don't change the protons. The protons are all the way inside the nucleus. And so this leads to an important point about the field of chemistry, which is that it deals with electrons. All the chemical reactions that we study have to do with electrons. Nuclear chemistry is that branch of chemistry that deals with the nucleus. But the chemistry that we do in this class is just shuffling around the electrons. So here are some examples. Neutral oxygen has a Z = 8. If it gains 2 electrons, it would have a charge of -2. Because now it would have 10 electrons and only 8 protons, and 8 minus 10 is -2. Sodium, which has Z = 11, if it loses an electron, now it becomes 11 minus 10 is equal to +1. So that is how you determine the charge on an element by tabulating the number of protons and electrons. If it has more electrons, it's negatively charged, it's an anion. If it's positively charged, it's a cation. So here's an example. Now you can play the same game and figure out how many protons, neutrons, and electrons with an anion. So here's O double minus. So the double minus means it has 2 extra electrons. So Z is 8. So 8 minus 10 is -2. And the number of protons is the same as the number of neutrons because the mass number is 16. So this is how you can figure out the numbers of protons, neutrons, and electrons in cations, in anions, and in the neutral elements. Okay, so let's go back to chatting about isotopes. An isotope is the same number of protons, but a different number of neutrons, as I said earlier. There is isotopic notation, a special notation used for representing isotopes. You have the symbol, so you're looking below at magnesium, that's the chemical symbol. And the mass number is in the upper left. That's the mass number. So that 24 is protons and neutrons. Notice there are 3 isotopes of magnesium, 24, 25, and 26. All of them have 12 protons, because if it didn't have 12 protons, it wouldn't be magnesium. But you can see in magnesium 24, it must have 12 neutrons. 12 plus 12 is 24. In magnesium 25, it must have 13 neutrons because it's still got 12 protons. And in magnesium 26, it has 2 more neutrons because it still has 12 protons. So these are all found in nature as a mixture. So if you collected magnesium in nature, usually bound up with a rock as an oxide, you would find all 3 of those isotopes present in natural abundance. So I'll go back to that slide. Here's another example of isotopes of hydrogen: protium, deuterium, and tritium. Here's hydrogen. Look at the mass number in the upper left. In the lower left is the atomic number Z. But once it says H, you already know that it has to have one proton. So you don't really need that subscript, but it's helpful. So we have protium, which is the only element on the periodic table that doesn't have a neutron in its nucleus. Only one in the periodic table. It just has one electron and one proton. It has a mass of 1 AMU. And look at this, in nature, 99.989% of it is protium. 99.989. These other two, deuterium and tritium, are much, much less. This is 1/100th of 1%, and tritium is much rarer than that. So you have the natural abundances of all three. It's not stated here for the magnesium, but all of the isotopes of any element have natural abundances. Now, here is the kicker. The kicker is that the atomic mass, as written on the periodic table, is the weighted average of all of the isotopes present in a naturally occurring sample. In other words, when you go back to the periodic table, let's go to magnesium. Look at magnesium, 24.31. That is the weighted average of magnesium 24, magnesium 25, and magnesium 26. Now, if the weighted average is 24.31, which one of these three isotopes do you think would be the most abundant if the weighted average is 24.31? It's the magnesium 24, isn't it? So the fact that the atomic mass is very close to magnesium 24 tells you that it's by far and away the most abundant. And the other two could be just like hydrogen, meaning present in very tiny amounts. But that's what these numbers are underneath all the elements. The atomic mass is the weighted average of all of the isotopes. Very important thing to understand. Now, the units here, as we know them right now, are AMU, atomic mass units. So all these first bullets here are telling you that the proton and the neutron have about one AMU. The electron is thousands of times less. So therefore, the atomic mass is equal to its mass number. Approximate. But what we really care about is understanding that those numbers are the weighted average of all the isotopes, and that most elements exist as a mixture of two or more. Okay. Now here is sort of the heavy math for this chapter. And what you're seeing here is how you determine atomic mass. So here is a formula. And that sign right there is called a summed, capital S, which is a sigma in the Greek alphabet, which means a sum. And you're summing the fractional abundance of the ith isotope by its isotopic mass, plus the next isotope, and so forth. Hey, this formula, I realize that not everyone will be able to unpack it. So if you look to the left here is a simpler version of the same formula. And then I'm going to do out a specific example. So this is called the average atomic weight of an isotope. And again, these are the numbers that appear on the periodic table. So A, which is what we're solving for, which is the average atomic mass, is equal to the fractional abundance of the first isotope. The 1 is the first isotope. The fractional abundance of the first isotope times its mass plus the fractional abundance of the second isotope times its mass plus the third plus the fourth, however many isotopes there are. You do the same thing. So here is a done out example. We have the element boron, and we're given, see that 10 as a superscript, that is the mass number. And we're told that 19.9% of boron is the boron 10, which has a mass of exactly 10.0129 AMU. 80.1, notice that 80.1 and 19.9 sum up to 100%. They always will. But there's boron 11, which is 80.1% of it, and it has one more neutron, so its mass is 11.0093 AMU. So these are the two pieces of information we need to apply this formula. Okay, so F1, M1, F1 is the 0.199. We're given the percentage abundance, but look at this important point. You always use the decimal percentage, which means you divide this by 100. Percent always means multiplying by 100%. So to undo that, to get to the decimal percentage, you would divide by 100, shift the decimal place 2 places to the left, and you have 0.199, which is F1, the fractional abundance of the first isotope, times its mass, 10.0129 AMU, parentheses, that's one term, that's the first term, plus the same thing for the second isotope, 0.801 times 11.0093. Now make sure, I urge all students to go in with your calculator. Oh, you can't see it. And type this in on your calculator and make sure you come up with 10.81 AMU. This ensures that you're typing in the numbers correctly on your calculator. A way to check your answer is the periodic table. 10.81, our value is 10.81. What does the periodic table say? Should say the same thing. Look at that, says exactly the same thing. Should be exactly the same thing. Proving to you that these numbers are the weighted average of all of the isotopes. So I have a couple of problems on here. And here's one that you can try to do on your own. Calculate the average atomic mass of oxygen. You're given the abundance, so make sure you divide all of these numbers by 100. And there is O16. So its atomic mass is 16. The atomic mass of O17 is 17 AMU. These are the atomic masses. And you're given the percentage of the percentage abundance. Need to convert those to decimal percentages. Go in and apply this formula. Now you have another term in there, 3 and M3 because there are 3 isotopes, and you'll come up with an answer. I did it all out for you, and you should come up with 16 AMU, which is what it says on the periodic table. Check your answer. And here is a third one, which I don't have the answer on here, but try it on your own. This is a level 2 or a level 3 type problem, not exactly the same as the other ones where you plug and chug, you figure out the atomic mass. This one is asking you, what is the atomic mass of the second isotope? If you can do this problem, you're really learning the material very well. Need to do some algebra here. Need to write this equation down. This is an equation, and you know you already know the atomic mass, and now you're looking for one of these terms. So that's my hint on how to do this more challenging problem than the other two. So that is how you calculate the atomic mass of an isotope. So I'm going to end it right here at section 2.4. And the second part of this lecture will cover those sections.